All right, so good morning, good afternoon, good evening. Welcome to our first Python bootcamp. I have been waiting this moment for almost 5 months since we announced the dev preview and finally is here. So please, Algo fam, share your expectation from this bootcamp in the chat. And today with me is the great Joe Polney, Senior Engineer at Algorand Foundation. How are you doing, Joe?
Hey, Camille. Hey, everyone. I'm doing pretty good. Much like you, I'm very excited for this. It's been a long time coming.
Awesome. And definitely all the Algo Dev, we are waiting for this moment and we are just around the corner. We are almost starting this event. But Joe, this is our first Python bootcamp. So please share with us what we can expect and what we are going to learn during these sessions.
Yeah, so in today's session specifically, we're going to get started with how we set up a Algorand Python project, and we're going to start developing our smart contract. And what we're going to be building is a smart contract for a digital marketplace or NFT marketplace. And then throughout the rest of the sessions this week, we're going to be building on top of that. So we're going to be writing tests using Python to test our smart contract. And then we're going to be using React to integrate our smart contract that we wrote into a front end in our later two sessions. So our first two sessions are going to be all Python and writing a smart contract and testing it. And then our last two sessions are going to be about integrating that contract into a front end.
Awesome. So we are going to have our first full dApp with the smart contracts on the front end and ready almost for production.
Exactly.
Wonderful. And I'm pretty excited because I really like Python. And now we are going to unlock a new superpower. Because you can create smart contracts in Algorand without having to learn a new programming language. And I have one alpha that I want to share with you guys. And in that way, you can keep motivated to join us in all the bootcamps. And I hope that you are ready for this. Please take a deep breath, 1 second. And who is ready to register for our upcoming global hackathon? Yes, in the next few days, we are going to announce our new global hackathon. And please stay tuned because I'm pretty sure that with the things that we are learning during this bootcamp, you will be able to participate. But do you agree with me, Joe, with the knowledge that we acquired during this bootcamp will be a good starting point to participate in the hackathon?
Yeah, definitely. Learning Python is going to give you a huge leg up in the hackathon because building with Python is so easy. And for anyone that hasn't yet learned Python on Algorand, of course, they can still participate in the bootcamp, but they're going to be using languages that are much harder to use than Python. So going into this bootcamp is definitely going to give you a leg up in the hackathon, and it should give you basically everything you need to know in order to be competitive in the hackathon.
What we are expecting that a lot of people participated in the upcoming bootcamps, and also that you maybe become the winners of the hackathon. So we are almost ready for the content that Joe has prepared for us, but we have some final announcement. So the first one is divided in 4 sessions. So today is going to be the first session. You will receive the Limestore links to join to the session, so you don't need to do anything else. If you are not registered for the upcoming bootcamps, you can do it. I will share with you on the chat the link. All the sessions are recorded and you will receive the recording once the sessions finish. And the important thing is at the end of the session 4, I will share the link so you can claim the certificate of completion. And I will explain you the process to claiming them and how you can add this verifiable credential to your LinkedIn profile. If you prefer to start building your smart contracts using TypeScript, we need to modify a few dates for the intermediate bootcamps. In that way, you will have more time to go through the videos, to try to create your own smart contracts, and also If you have questions, you can join the Discord, and the most important thing is to start learning together. Last important thing to remind you is please help us to share screenshots of these sessions, tagging us on X, and in that way more people can join and become algorithms.
So before we get started, I just want to talk a little bit about the prerequisites. So this whole week, we're going to be assuming that you have your AlgoKit environment already set up. Now, if you are here right now and you don't have your environment set up, you can go to the YouTube channel that Camilo just directed you to, and we have various setup videos there. Or you can subscribe and stay tuned for our recording of our intro bootcamp, which also goes over setting up your developer environment. What we need to make sure our environment is ready to go is we're first going to run our command algokit doctor, and we want to make sure that this command runs. And importantly, we want to make sure that it's seeing Python version 3.12.3. This is really important because Algorand or Python for Algorand requires Python 3.12 or higher. If you attended the intro bootcamp, you should have this already set up. If not, don't worry, these sessions are being recorded. I'm not going to pause and take time now to go over development environment setup, but you can use those resources to get set up and then come back and catch up with the recordings. So once you've verified that you have AlgoKit installed and you indeed have Python 3.12, after running AlgoKit Doctor, one thing you also want to do is make sure you can run a local net. Now, we won't necessarily be using this today. So if you don't have it today, that's fine, but you will need it later on in the week. So if you do an AlgoKit local net start, you should make sure that you see it has started, and you can verify this by running AlgoKit local net status. Okay, and if AlgoKit local net status and your AlgoKit local net start are working, then you should be ready to go for getting started with Python. So throughout our entire journey developing on Algorand, we're going to be using AlgoKit. So it's important that we have all those tools set up in your environment. And again, if you don't have them yet, don't worry, this will be recorded. So you can go set up your environment and then come back later to catch up with the recording. So with that out of the way, I'm going to go ahead and play the bootcamp content for writing our Python smart contract, starting with AlgoKit Init. And in order to get to all of our bootcamp content, come to github.com/AlgorandBootcamp. You will see a link to our intro bootcamp, and then eventually this bootcamp and our following bootcamps will be posted here. Right now, what's here for the full stack bootcamps is our previous bootcamps. We'll be updating this shortly today with links to our new bootcamps. But the intro, if you just come down to intro bootcamp, click on the repository, and here you can find the intro bootcamp. And now, I think we got no more questions. So let's go ahead and get started. And again, just a reminder, if at any time you feel like you're falling behind, we're going to try to answer questions live, but this is recorded, so you can always catch up later.
Hey everyone, Chris Kim here, dev role for Algorand, and today we're going to do a complete walkthrough of implementing a basic digital marketplace smart contract using Algorand Python. With AlgoKit 2.0, we can now write smart contracts with native Python, so you no longer need to learn a new smart contract language to build an application using blockchain. By the end of this video, you'll know how to use AlgoKit to initialize a project and write a complete and functioning digital marketplace application. So, let's get started. To initialize my project, I'm going to use AlgoKit. If you don't know what AlgoKit is, make sure you go check out the AlgoKit videos on the Algorand Developers YouTube channel, and make sure you have it downloaded to follow along with this video. To initialize a project, we're going to use AlgoKit Init. Now, this command is going to start an interactive wizard that will ask you a series of questions to set up your project. The first question is going to ask you what kind of project you want to build. And we have multiple options here, smart contract, front end, or both smart contract and front end. And for this video, we're only going to focus on building the smart contract. So I'm going to choose the smart contracts option. Then it's going to ask you what language you want to write your smart contract, and I'm going to choose Python. Then it's going to ask for the name of the project, and I will name this Digital Marketplace. Then it's going to start rendering the template, and then it's going to ask for the name of the app, and I will name this Digital Marketplace as well. Then it's going to ask you what template preset you want to use. You can either choose the starter preset or the production preset. Now, for starter, it's more for playing around with the template or experimenting certain features, and production template is more for actually building an application. Since we'll be building an actual digital marketplace with the front end, I will choose the production template. Then it's going to ask you what deployment programming language you want to use, and I will choose Python for this as well. Then it's going to ask you, do you want to run allocate project bootstrap? Now I'll say yes to this because the allocate project bootstrap command is the command that is going to install all the dependencies that you need to build with Algorand Python. So as you can see, allocate is setting up the development environment for me. Allocate bootstrap also do a bunch of stuff like creating a .env file for you and just basically setting up your development environment. So whenever you're starting a new Algorand project, you definitely want to run the allocate bootstrap command. Finally, it asks you if you want to initialize a Git repository, and I'll say yes to that. After you're done with the init process, if you have VS Code as your default editor, it will automatically open VS Code for you. So this is the created allocate Python template from allocate. And if I make this bigger and go to the file explorer, you can see all of these files pre-configured for you. Now the README file contains a bunch of instructions and details about this template. You can definitely take a look at this later when you're building your project, but for now, I'll just close it. When allocate opened this VS Code editor, it opened this project in a workspace mode. Now, when you create an allocate project, you can have multiple projects inside of one allocate project. But the problem is if you have multiple projects, it can mess up your development environment when you're trying to work with multiple projects inside of one editor. So if you open up your allocate project in workspace mode, it will divide up those projects into individual containers, and you'll be able to work with them in an independent manner. So for now, since we've initialized the smart contract Algorand Python template, it only has the digital marketplace folder here. But if we add a front-end component, we could have another folder called front-end under the same allocate project. So let's now go inside of the digital marketplace folder and go to the smart contracts folder. Inside of here, there's another folder called digital marketplace. If you open that up and click on contract.py, you will see the default smart contract that comes with the Python template. So as you can see, there's a Python class named digital marketplace, and it's inheriting the arc4 contract class, where we import that from the AlgoPy module. By inheriting the arc4 contract class into the digital marketplace class, we're saying that this smart contract is an arc4 compliant smart contract. Arc4 is an Algorand standard that specifies the ABI specification that makes your smart contract more interactable from the front end or a client, and it also automatically handles the routing of your smart contract calls. So using arc4 contract is definitely the way to go. But if you prefer to not use the arc4 standard, you can just manually specify an approval program and a clear program inside of your Python class and do it that way. All right, let's get started. First, just going to delete this hello method that comes with the template so that we can start from blank state. The first thing I like to do when I'm coding with Python is I'm just going to import everything here by saying import star, just so that I don't have to manually add what to import while I'm coding. So I just like to have everything available while I'm coding, and after I'm done writing the smart contract, I'll come back and specify specific imports to follow the best practice. Okay, so here's what we're building. This digital marketplace contract is going to allow the contract creator to list an asset on sale. So anyone who wants this asset will be able to purchase it by paying the smart contract and receive the asset. The creator will then be able to delete the smart contract, which will return any leftover assets and transfer the profits gained from sales. So first thing I like to do is I like to list out all of the class methods that is required to build this basic digital marketplace. So the first method is going to be the method that is going to create the application. We also need a method where if the seller wants to update the price after they create this smart contract, we want to have a way to do that. So we want a method that will be able to update the listing price. And then the next thing we want to implement is an opt-in method. Now, this is a specific feature on Algorand where if you want a smart contract or an account to receive and hold an asset or a token, you need to opt into that asset. Opt-in is like a spam prevention feature on Algorand. So if your account is not opted into an asset, nobody can send you that asset to your account. But on the low level, what's happening is that when you opt into an asset, the account is saying to the ledger that, hey, I want to rent this space out to hold this asset. So for the seller to send the assets that they want to sell to this digital marketplace smart contract, the digital marketplace smart contract needs to be opted into that asset. So this is the method that's going to do that, and it's going to opt in to the asset that will be sold. Okay, so now we have a way to opt into the asset and be able to deposit the assets that we want to sell to the smart contract. Now we need a method to buy the asset. And this method will be called by the buyers who want to buy this asset. Last but not least, we need a method to delete the application. So the way this smart contract works, the life cycle of this smart contract is that whenever a seller wants to sell an asset, it will create a smart contract, opt into the asset, and deposit that asset to sell. People will buy the asset, and once the seller is done selling, they'll be able to delete the application and get the profits from the sales. Amazing. So these are the 5 methods that will be required to implement this basic digital marketplace. So let's first start with the method to create the application. Now you will define a class method like any other Python method, and I'll name this createApplication. And because this is a class method, I'll have self as the first parameter. And then while I'm creating the application, I also want to set the asset ID, the asset that will be sold from the smart contract, and the price that I want to sell at. So I want to pass in the asset ID of the asset I want to sell and the unitary price. And this is going to return nothing. Amazing. But before we move on, we also need to set the type of these parameters. The asset ID's type is going to be an asset type. The type asset is a reference type. So on Algorand, we have the blockchain ledger, right? But whenever a smart contract method is trying to access the blockchain ledger, it doesn't gain access to the entire ledger, but the application call that is calling the smart contract method must specify what references that it wants to include that the smart contract method needs to really execute its logic. So by passing in the asset type in the variable name asset ID, we are referencing the asset with that asset ID when we are calling the createApplication method. So the smart contract will now have access to the asset that is recorded on the Algorand ledger. And it knows that it has to do something with this asset. So that's when you pass in reference types into a contract method argument. Later on, you will see different contract methods with arguments that has a transaction type, which are also reference types. I'll explain more in detail on what those look like later in the video. For the unitary price, we will set it as a uint64 type because it will be a number. Now this uint64 is also a specific Algorand type that the AVM understands, where AVM stands for Algorand Virtual Machine. The AVM understands two data types, bytes and UN64. So whenever you can work with either of those types, you want to do that because that is the most efficient way to handle these data types. But with ARC4 contracts, it also supports various other data types that will be automatically encoded and decoded into the AVM basic types. But here, since this is a number, we're just going to use the AVM UN64 type. Now, while creating the application, I wanted to set the asset ID and the unitary price, and I can do that by doing self.assetID is equal to asset ID, and self.unitary price is equal to unitary price. But for this to work, I also need to specify on the class level what the data types of these states will be. So for asset ID, I will set that as uint64. And by just saying uint64 here, this is implicitly saying that asset ID will be a global state. Now in Algorand, there are three different types of state: global state, local state, and box storage. Global state is state that is available on a global level within the smart contract, where local state is a specific state that is recorded on the account level, where each account that is opted into the smart contract can have their own specific state. Box storage is a bigger, unlimited, on-demand state that you can use if you want to store more data on demand. But since asset ID and unitary price, they're...
All right, hey everyone, just wanted to pause real quick to, why can't I? Pause real quick just to answer this question. So just to clarify some of the terminology here. So when we say Python on Algorand, the language that we're writing is actually just Python, as you can tell so far. But the way that we write that Python is using a Python library called Puya. So the language we're using is still Python, but the library that enables us to write in that language is called Puya. So we're using the Puya compiler to convert our Python that we're writing into the TEAL code that the AVM understands. So Puya is the name of the compiler, but we're still using Python at the end of the day. So when you see Puya, that just means Python on Algorand. For you as a developer, you are basically just going to be interacting with AlgoPy and writing Python as per usual. But if you see Puya, that just means Python for Algorand.
Unitary price, they're both simple state that should be available to the entire smart contract. I'm going to set them as global state. And for asset ID, I set that it will have the data type UN64. And also for unitary price, I will set that as UN64 as well. Great. Now there's one more thing that I need to do here to make this a valid method for a smart contract. And that is to add this decorator at arc4.abi method, where the action that we want to allow is a no-op, and the create should be set to require. Now, let me explain what this is doing here. By decorating a class method with arc4.abi method, we're saying that this method is externally available for someone outside of the smart contract to call, and it is an ABI method. Now within the parentheses here though, we set allow actions equal to no-op, where no-op stands for no operation. So on Algorand, there are various different types of transaction types, and one of the transaction types is application call. And this specific transaction type is used when you're calling a smart contract. And for application calls, you can also set various different onComplete parameters, where onComplete are side effects that happen along with the application call. So for example, if the application call has an onComplete set to opt-in, that application call, along with calling a contract method defined inside the smart contract, it will also opt in the account to the smart contract. Another example, if an application call has an onComplete parameter set to delete application, then along with calling a class method defined in the smart contract, it will also delete the smart contract. But here, since we said that the onComplete is set to no op, no operation, this is just a simple application call that doesn't have any side effect. But by setting create equal to require, we're saying that this no operation application call is a special type of an application call that creates the application. So this decorator right here is saying that this create application method is a special type of a method that is used to create this smart contract. All right, before we continue on, let's first try compiling this smart contract so that we know that we're doing everything right. So I'm going to open up my terminal. Let me just close this. And to compile the smart contract, I'll run algokit project run build. And there you go. You can see that the smart contract was successfully compiled. So whenever you want to compile your Python smart contract, you just want to run algokit project run build, and it will automatically compile your Python smart contract into TL code. And to see what happens here, if you go to the file explorer, we can see that this artifacts folder was created under smart contracts folder. And if I open that up, we can see these 4 files were automatically created.
All right, I'm just going to quickly pause because I'm seeing a couple of questions about setting up your developer environment. So when you run an algokit init, it should by default set up a Poetry virtual environment for you. So what I'm going to do, I'm going to minimize the video for now. I'm going to share my screen. Let me zoom in a bit. I'm just going to go into a temp directory here. I'm going to do algokit init, then smart contracts, Python. Okay, so I'm going to choose the production and choose Python. And this is important. I want to make sure that I click yes to algokit's project bootstrap. And that'll go ahead and install my dependencies. And we're going to open that up. Oh, that opened another window. So let me share this new window. So in this new window now, what should happen is that it created a virtual environment using, if I do a Poetry install, yeah, so if you do a Poetry install, that's when you should get a .vm. Now, typically this should be done by algokit bootstrap, so I'm not sure why it wasn't. So if we want to make sure we can run an algokit bootstrap all, algokit project bootstrap. Oh, there we go. So that's the command we want to run in order to initialize it. So if you're having problems setting up your VS Code environment, you want to make sure you run this command. So let me copy this to the chat. Okay, so I'll get bootstrap all. And after that, if you're still running into issues with AlgoPy not being found, so if you come into your contract and it's not finding AlgoPy, what you might need to do is in the bottom right here, select interpreter. And we're going to use our VM, and we are going to enter your interpreter path, and we're going to come to digitalmarketplace.vm bin and select Python. Okay, and now at this point, we've set up our project. So If you are running into issues with VS Code, make sure you do a AlgoKit project bootstrap all. And then if it's still not finding your proper environment, then just make sure you select that in VS Code down here in the bottom right. Okay, so yes, this is in the video, it noted that this is an expected error. We're going to be fixing this out later on in the video. So for now, you can ignore that error. We're going to be fixing that later in the video. So don't worry about that. For now, we can just continue writing, even though it might not build yet, because Chris, when he was recording this, forgot to save. So he just needs to fix that typo later, which he will be doing. So we can continue on, even though we have that error, at least for now. The last step, so you only need to do this if your VS Code isn't working. To me, sometimes it can be a little bit inconsistent with Python, depending on how you have it installed. Like in my case, I use ASDF to manage all of my software. So sometimes VS Code has a hard time finding it. So what you need to do is, let me share my screen again, is you need to make sure, if you see in the bottom right here, where it's like a warning that says select interpreter, you're going to come down here and you can, oh, actually it looks like there's already a VM in root. So you can just select the root VM and select that. And that should then get you set up to tell VS Code which VM to actually point to. So in Python, basically every project that you create, you have what's called a virtual environment in order to isolate all the dependencies for that project. So what we need to do is make sure that VS Code understands which virtual environment we're using. And you do that by clicking on the bottom right here and choosing your VM. Okay, but again, you only have to do that if you're running into errors in your IDE. For the most part, like shown in the video, that should be done automatically for you when you do an AlgoKit init.
The digital marketplace.approval.teal is the teal code of the approval program of my digital marketplace smart contract. So as you can see, this is the teal code of the Python code that I wrote. And this teal code is what the AVM understands. But thankfully, us as a developer, we don't really have to worry about what this means, and we don't really have to directly work with teal code. The clear.teal is also the teal source code of the smart contract. Like I said, Algorand smart contract consists of approval programs and clear programs, where clear programs are only called whenever someone is calling a clear state application call. Then we see this arc32.json file. Now this is the ABI specification of our smart contract. You can think of this as like an instruction or a specification of our smart contract that has all the details that a front end or a client that wants to interact with our smart contract needs. And then we also see this client.py file automatically generated. Now this is a typed application client that was auto-generated using all of the information available inside of this arc32.json file. And this client will be used when we are writing our deploy script, interaction script, whenever we're writing code that interacts with the smart contract inside a front end, and so on. You'll see how this automatically created application client will be used later when we're testing the smart contract that we built today. All right, back to the smart contract. Now let's implement this second method here that will update the listing price. This method should be externally callable, and it should be called by the creator's account to update the listing price. Now, because this is an externally available method, we want to decorate it with arc4.ABI method. And in this case, because we're not doing a specific method here, we don't need to specify any configurations here. And I will name it SetPrice. And it will take in the self parameter and the unitary price that I want to update to. And it will have the uint64 type. And this is going to return nothing. And to update the price, all we want to do is do self.unitaryPrice is equal to unitary price. And that will update our global state. Now there's one big problem with this code right here. Currently, the SetPrice method doesn't have any authorization logic. So anyone will be able to call this SetPrice method. So if a bad malicious actor comes in and say, hey, I want to make the price 0, make it free for everyone, they could do that because anyone can call this method right now. So we need to make sure that this is only callable by the creator of this smart contract. And to do that, we want to assert that the transaction.sender, which is the sender of the application call that calls the SetPrice method here, is equal to the global.creator address. The global.creator address specifies the address of the creator that deployed this smart contract. So by having this assert here, we're saying that this SetPrice can only be called by the creator's address. Amazing. Let's compile that and see if everything works perfectly. And boom, it works. Great. On to the next one. This method right here is a method that should only be callable by the creator, and the creator should call this method to make sure that the smart contracts account is opted in to the asset that the creator wants to sell. So, because this is an externally available method, we will decorate it with arc4.abi method, and I will name this OptInToAsset. It will take the self parameter again, and this time for the parameter, it's going to take in an MBR pay, which has the type gtxn.payment transaction. Now, this payment transaction type is a reference type, and this is referencing a payment transaction that happens alongside with the application call that calls the OptIntoAsset method. Now, I'll talk about this more later when I'm implementing this method right here. And this method is not going to return anything. Okay, so for the smart contract to opt into the asset, it needs to send a 0 asset transfer. Because to opt into an asset, all you do is send an asset transfer transaction that sends 0 amount, and you send that to yourself. So for the smart contract to send transaction, it uses what's called an inner transaction. An inner transaction is any type of transactions that is initiated by the smart contract. So to implement an inner transaction, you do itxn, and here we want to do an asset transfer. But here, as you can see in the IntelliSense, these are the different types of transactions that you can use here. But for now, I will do asset transfer. And like I said, first you want to define the asset that you want to transfer, which is self.assetID, asset receiver, set to itself, so this smart contract's address. So we do that by doing global.currentApplicationAddress, and asset amount, which is set to 0. Great, so we created the asset transfer object, and now to submit that, we want to do .submit here. Amazing. So let's take a look at what we're doing here. We've created an inner transaction, which is an asset transfer transaction type, and we're saying that the asset that we want to transfer is an asset that has this asset ID, which is stored inside of our global state over here. Oops, I noticed something that I did wrong here. So what I did wrong here is that when I was passing in the asset ID here, I set the type as asset type, but the global state that is storing the asset ID is set to UN64. So we actually need to extract the asset ID inside of this asset type. So to do that, we do assetID.id. And that is going to get the UN64 type of the asset. So coming back down here, so that's how we specify what asset that we want to transfer. We also set the asset receiver set to this smart contract's application address. Now, on Algorand, the smart contract itself is not an account. That's why the smart contract has what's called an app ID, which is a unique identifier of the smart contract. But to send tokens to the smart contract, you're actually sending it to a linked application account. So every Algorand smart contract has an associated application account. And to access that, we do application address and not application ID. So that's why doing current application address here. And then finally, we set the asset amount equal to 0 because that's how you do an opt-in transaction. But there's another thing that we need to consider here. Whenever you're opting into an asset, you need to pay the minimum balance of holding an asset because you're basically renting a space on the ledger. So you have to pay for that rent. So that's why we are grouping this payment transaction with the OptIntoAsset method call. So by passing in this payment transaction reference type here, we are saying that to call the OptIntoAsset method, you need to atomically group and send a payment transaction as well. But right now, we don't know what this payment transaction is doing. It just says that this MBR pay is a payment transaction. We don't know how much, we don't know who we're paying and who it's coming from. So we need to write some logic here that specify that this MBR pay is an actual payment to the smart contract to cover the minimum balance to opt into the asset. So first thing we want to assert is that we want to assert that the transaction.sender, the account that called the OptIntoAsset method, is the creator of the smart contract. So we do that by doing global.createAddress. Next, we want to assert that the smart contract is not already opted in to the asset. So to do that, we want to do assert not global.current application address is opted in to the asset, which is self.asset ID. So this code right here is saying that you want to assert that the current application account is not opted into the asset with this asset ID that is stored in the global state. Great. Now let's make some assertions for the payment transaction. We want to assert that the receiver of this payment transaction is indeed this smart contract. So to do that, we want to do MBR pay.receiver is equal to global.current application address. The next thing we want to make sure is that this payment transaction is actually sending the amount of algos to cover the minimum balance to opt in to this asset. So you want to do assert MBR pay.amount is equal to global.min balance plus global.asset opt-in min balance. So let's see what's happening here. We're saying that the amount of the payment transaction of MBR pay is equal to the minimum balance where we got that from the global class. And this global class contains all the global variables available. And this min balance is the minimum balance that the smart contract needs to become an eligible account on the Algorand ledger. And on top of that, we want to make sure that this smart contract has enough to cover the minimum balance of the asset opt-in. So with this one payment transaction, now this digital marketplace smart contract has enough algos on this account to cover the minimum balance to become an eligible smart contract and the minimum balance to hold an asset. Great. Now let's save that and let's build it to make sure we did everything correctly. Great, everything works. Now let's go to the next method where we are going to define the method that buyers are going to call to buy the asset. Now again here, because this is an externally available method, we want to decorate it with arc4.abi method. And we will name this buy. and this is not going to return anything. And just like any other class method, it should have self as the first parameter. And it's going to take in another payment transaction here, and we're going to call it buyer transaction, which has the payment transaction type and the quantity that the buyer wants to buy, which has the UN64 type. Great. Now, again, the reason why we're including the payment transaction here is that we're saying, hey, to call this buy method, you need to atomically group payment transaction with this method call. So the actual transfer of algos to buy the asset is not happening inside of the smart contract logic, but it is a separate payment transaction that is atomically grouped and atomically executed along with the method call here. Great. Let's start by defining some asserts. First, let's assert that the unitary price defined stored inside of the global state unitary price here is not equal to 0, just to make sure that we are not giving away free stuff. So we will say assert that self.unitary price is not equal to uint 64 0. The reason why we're wrapping the int type 0 with uint64 is because the unitary price has a data type uint64, and in Python there is no way to automatically detect this int type and automatically encode it into uint64. So we're specifying here that this is a uint64 type. Next, we want to assert that the account that called the buy method is also the account that sent this payment transaction. So to do that, we want to assert that txn.sender, which is specifying the account that called the buy method, is equal to buyer transaction.sender. Next, we want to assert that the receiver of the payment transaction is indeed this smart contract. So to do that, we do assert buyer transaction.receiver is equal to global.current application address. Last but not least, we want to assert that the payment transaction amount is equal to the unitary price. So to do that, we do assert buyer txn.amount is equal to self.unitary price. So we want to get the price of each unit, and we want to multiply that to the quantity variable that we get from the parameter over here. So this is saying the amount of the payment transaction should be equal to the price of each unit times how many of the asset that the buyer is trying to buy. So if the buyer wants to buy 10 assets, it will be 10 times the unitary price. Amazing. So after all these asserts, we now know that the atomically grouped payment transaction is indeed legitimate payment transaction that is buying the asset from the smart contract. So all we need to do is write the logic that will send an inner transaction to transfer the asset to the buyer. So to do that, we do itxn, and then we're going to do an asset transfer. We're going to say that the asset that we want to transfer is the asset stored in our global state, self.asset ID. The asset receiver should be txn.sender, and the asset amount should be the quantity. And then we do .submit to actually send that asset transfer. Amazing. So just to explain how everything is working here, we've implemented a buy method, which should be called by the buyer. And when the buyer is calling this method, it will also send a payment transaction that is atomically grouped with this method call. And the buyer is also going to specify how many assets that it wants to buy. We're going to first assert that the unitary price is not 0, so that we're not giving away free stuff. And then we're asserting that the account that called this method is also the sender of the payment transaction. The receiver of the payment transaction is the smart contract address. and the amount of the payment transaction is indeed enough to cover the price of the asset. And once everything is approved, the smart contract will send an inner transaction where it's going to transfer the asset with this asset ID. The receiver of this transfer will be the transaction.sender, and the amount will be the quantity specified by the buyer. Amazing. So now we've implemented everything to deposit the assets that the seller want to sell and the method for the buyers to buy the asset. So the feature of the digital marketplace is all implemented. Now all that's left is a method that the creator can call to delete this smart contract. Now since this delete method is externally available, we'll decorate it with arc4.abi method. And since this application call is a special type of an application call that's going to delete the smart contract, we will specify allow action set to delete application. So this is an application call that has an onComplete set to delete application. So it has a side effect that will also delete this smart contract after calling this method right here. Amazing. So I'm going to name this delete application. It's going to take in the self parameter and nothing else, and it's going to return nothing. Now, when we are deleting the smart contract, we want to do a couple actions before we delete the smart contract. First thing we want to do is, let's say the seller deposited 100 asset into the smart contract to sell, but nobody was really interested in buying the asset, so only 50 of them were sold, and 50 is still left in the smart contract account. In that case, if we delete the smart contract without withdrawing that amount, the seller will just lose the asset. So we want to make sure that we withdraw all of the leftover assets that weren't sold to people. Second thing we want to do is we want to withdraw all the profits that were gained from sales. So when people bought these assets, they sent algos to the smart contract account, and the profits is locked up in the smart contract. So when the seller is deleting the smart contract, they should also withdraw that profit from the smart contract to its personal account so that they can enjoy the profits. So let's implement those two features. First thing we want to do though is to make sure that this is only callable by the creator's account, because if anyone's able to delete the smart contract, they can steal the profits, they can delete the smart contract before any sales happen, and so on. So we want to assert that the sender of this transaction is equal to the creator account. Now let's implement the first feature to withdraw all the leftover assets. So to do that, we want to send an inner transaction, which is an asset transfer. We're going to transfer the asset that has self.asset ID, and the receiver of this asset transfer should be the creator's account. Now, when we're specifying the asset amount, this value could change based on how many assets are left in the smart contract. So what we're actually going to do here is we're going to set this equal to 0, and then we're going to add another configuration here called asset close to. And we're going to set this to global.creatorAddress. Now what this asset close to is doing is that it's saying, hey, when you're sending this asset transfer all of the remaining balance of this asset that we're transferring to the creator's address. So regardless of asset amount being 0, because we set this close to parameter, this asset transfer is going to transfer all of the remaining assets that is inside of the smart contract account. So this is how we ensure that when we're deleting this application, the seller is receiving all of the unsold assets back into its personal account. So that's how you create the asset transfer, and we submit that by doing .submit. Now let's implement the second feature. And this second feature is to withdraw all the profits that are locked up inside the smart contract. So to do that, we're going to send another inner transaction, and this one will have a payment type. We're going to say that the receiver of this payment transaction is going to be the creator's address, and we're going to set amount equal to 0 again. And this is because we're going to add another parameter called close remainder 2, and that's going to be set to global.creatorAddress. So what's happening here is, again, we're sending a payment transaction from the smart contract, and the receiver of this payment transaction will be the creator's account. And even though we set the amount equal to 0, because we've added the close remainder 2 parameter here, we're going to send all of the remaining algo balance inside of the smart contract account into the creator's account. So this is how you make sure you transfer all of the algo balances, including the minimum balance that we sent over here in OptInToAsset. This payment right here, this sent the minimum balance of the smart contract and the minimum balance to hold one asset, right? So when we're sending this payment with the close remainder 2, this is also going to include those minimum balances and send it to the creator. And we're going to submit this. So by having these 2 inner transactions here, we're going to completely remove all the assets and all the algo balances from the smart contract account before deleting the smart contract. So to understand the process, by having this delete application set to an ABI method with onComplete set to delete application, when the creator calls this delete application method, it's first going to go through this logic. And after completing all of the logic defined inside of the smart contract, it's going to delete the smart contract. Amazing. Now let's try building this smart contract to make sure we've implemented everything correctly. And there you go. It compiles perfectly. And we now have a functioning basic digital marketplace smart contract written with Algorand Python. In the next video, now we're going to test the smart contract that we built. And we're going to write a deploy script that is going to deploy the smart contract to a local network, call all of these lifecycle methods, and make sure all the methods work like we want them to. So I'll see you in the next video.
All right. So as Chris mentioned, that concludes the content for today. Tomorrow, we will be getting into the actual testing. So now that we've written the contract, how do we interact with it? And that will not only help us test the contract, but help us understand how we just interact with the contract in general. So we'll be covering that tomorrow.
Yeah, so thanks, Joe, and all the DevRel team for this interesting session 1. And maybe the first time that we try to build our own smart contract, we feel like we don't understand everything, all of this bootcamp, to create a working example that will help us to build our own solution. And for example, in my case, I play with Python a lot the last week, and I really enjoy, for example, mixing Algorand, Python, and Arduino. And I create a basic example that allows you to interact with a LED that change the state depending on the information that it reads from the smart contract. And if I can do it, I'm not a developer, obviously you can do it. And for example, today we learn how we can start a project using AlgoKit, how we can code some functions, how we can save information in the global state, how to buy an asset, how to transfer an asset. And it's important to add those security validation that are fundamental in a production contract. So our mission is to review the recording, replicate the example, and try to add our own functions. So I don't know if we have questions. This is the time. We have over here Joe and Giorgio that can help us to solve the questions that we have. So we can take a look on the chat. Okay.
Yeah, I have seen a couple of questions along this line, right? So we wrote our contract to basically accept when we started, we pass in an asset ID. And because we're just passing in the asset ID, that asset ID can be anything we want. So we can either, when we start our contract, we can either create a whole new asset just for the marketplace, or we can take an existing asset that already exists and list it for sale using the same logic. So the logic allows you as the person deploying the contract to define which asset you're selling. Now, right now, the way we have it implemented, the only token you can use to actually buy the asset is the algo. But if you wanted to, in that buy method, right now we have it accept an atomic payment transaction. You could also have it accept a atomic asset transfer transaction and use that in order to accept different currencies for your token. But that's a bit more advanced, and we're not going to be covering that in this session, but it is definitely possible.
And that is a super useful use case because you can pay with USDC. So a lot of people prefer to create a solution where the people can pay with stable coins.
Exactly.
Okay, my friend, we don't have more questions. So I learned a lot during this first session. Thank you all for joining us today and looking forward to seeing you in tomorrow's session. Something else, Joe, that you want to share with us today?
No, I think that's it. Thanks, Camilo. And also shout out to Chris Kim, who recorded that video. Wasn't able to join us live here, but he is going to be all over the AlgoDevs YouTube channel. So if you haven't yet checked it out, definitely do, because we cover a lot of topics beyond just the bootcamp there. So definitely check it out and give him some love. Also today we have Giorgio with us, helping us answering question on the chat, and he is doing an amazing job. So thank you, Giorgio. So yes,
thank you, guys.
Thank you, Giorgio, for being the Python expert.
Yeah, I know it. Thank you so much. See you tomorrow.